This is Honors Algebra 2 Pre-Calculus. We're still doing 2.6 in Algebra 2. This is part 3, which talks about step functions. So your textbook's actually going to introduce a couple different step functions. In reality, in most of math, you're going to find that there's only one, and we'll talk about that. But for notation purposes, in case when you're doing homework in your textbook, I want to introduce you to the 3 different notations that you're going to see for step functions and what they mean. So a step function is essentially a rounding function, and you're going to see these on page 125 in your textbook. Okay, so let's get started here. Cool. All right, so in page, oh, I'm in blue. I didn't expect that. Okay, well, in page 125 of your textbook, you're going to see step functions. So step functions are so named because they look like stairs, right? So they actually physically look like steps when you graph them, and we're going to walk through a couple of those in a second. So let's start with the 2 that your textbook introduces, and then we'll talk about which one of them is actually like more of a thing because they're not really both particularly common. Okay, so the primary step function that we're going to see is what's called the greatest integer less than function. So greatest integer, that's not how you spell greatest. It's harder to rewrite on here. Greatest integer less than, okay, function, which in your calculator is going to be abbreviated int, but in your brain, you can think of this as a round down function, okay? And I'm sorry that I'm just now getting used to writing on this thing, but I'm trying. So your brain can think of it as a round down function. So here's what this looks like, okay? So the greatest integer less than function, if you see brackets with an x inside them, what that's telling you to do is that's telling you to round x down to the nearest integer. Now, if x is an integer, so nearest integer, okay, it is the same notation, okay, that I've only ever seen in your textbook, to be honest, as this weird bottoms only bracket, okay? I've never seen that notation anywhere but your textbook. You're going to see it as a full bracket, but your textbook uses this weird bottom only bracket. So what that's telling you to do is it's telling you to round whatever number is on the inside down to the nearest integer. And that means that if something's already an integer, it rounds down to itself. So if I had brackets around a 2, 2 is already an integer, it's still going to be a 2. One way to think about that is if you look at a number line, let's say there's 1, there's 2, it's already on the integer, right? But if I gave you something like 2.3 inside the brackets, that's also going to round down to 2, because if you look at where 2.3 lives, here's 2, here's 3, 2.3 lives somewhere around here, so it rounds down to the nearest integer, right? But that would also be true if I pick something like 2.9. Now you would think, oh, 2.9, that rounds to 3, but not if you're in the round down function, because it's the round down function for a reason. 2.9 lives somewhere around here, round down to the nearest integer, it's a 2, right? Now, where people tend to get confused on these, and again, note that this notation with the bottom only bracket is exactly the same thing. It's a weird notation that only your book usually shows, but don't be thrown. So if I had written any of these with just a round down, like if I had written that last one as a 2.9 with this weird bracket that has a bottom only, that would be the same thing, okay? It means the same thing. Where we start to get screwed up on these round down functions is when we talk about negatives. It really helps me personally to draw the number lines like this. You don't have to feel that way. And again, notice that the reason it rounded to a 2 in that first one was because it was already a 2, right? But let's say I had negative 3.8. Well, a lot of us would think, oh, I'm rounding down, so that should be a 3. That's the smaller number. But that's not true, because if you look, here's where negative 3 lives. Here's where negative 4 lives. Here's negative 3.8. You're rounding down, so you are rounding to a negative 4, okay? That's what the round down function looks like. Now, in your calculator, because it is called the greatest integer less than, so I'm going to highlight that it says integer, in your calculator, this is called the int function. It's int and then parentheses. So you're not using brackets, it's int. So I'm going to show you how to find that in a sec. But before we do that, let's talk about the other function. So the other one that your book introduces that honestly you're not going to see very often. What's funny about this is actually, although you don't see this very often, you see it a lot more in the real world, just not as a notation. Really, this is the only one you're going to see in the real world. But the other one that your book introduces is what's called a round up function, right? So the round up function. And just like they have this weird notation where they use the bottoms only bracket that you really only see in this book, they're going to use a top only bracket for that, okay? And that's the same exact scale, except you're rounding up to the nearest integer. So if, for instance, I had a 1.1 in a round up, sorry, that shouldn't have the bottom bracket. It's just that it's hard to erase things in this, and I'm only just learning. Okay, so if you look at where this lives on a number line, right, this is between the number 1 and the number 2, right, because 1.1 is right here, and this is the round up function, so you're going to round up to 2, okay? Now, round up functions in the real world happen all the time. I don't know how it works with cell phones, but when I was a child, I know that if you, we had landlines, because, you know, I'm basically a dinosaur. And if you had to call like long distance and you went a hair over a minute, like if you were paying so much for long distance per minute and you went a minute at a single second, you were already paying for the full second minute. That's a round up function, right? That's saying you didn't actually talk for 2 minutes, but the second you pass 1 minute, we round up to 2 full minutes. The second we pass 2 minutes, we round up to 3 full minutes. And there's other things that definitely do that. But so in businesses, round up models are actually a lot more common because they want to charge you more money, right? So that's a thing. But again, what you'll see is that there is no round up function in your calculator for a reason. Essentially, the round up function is what happens if you do some transformations, which we're going to learn about in 2.7, on the integer function, the greatest integer less than function. So really, in your calculator and in most computer systems, there is no quote-unquote round up function. There is in this textbook, there is a notation for it, so I want you to be familiar with it. But in reality, what we're going to learn in 2.7, which is our next section, is how to perform transformations on the greatest integer less than function, which is actually the real function, this guy right here, so that it does the whole round up thing for us. So anyway, let's do a couple more round up things. And then we're just going to walk through some examples and we'll talk about what this looks like as a graph. So let's say I asked you to round up, I don't know, let's do 3.9, right? Now this intuitively is actually going to round up the same way that it would anyway. It's going to be a 4, but here's the reason. If you put a 3 and a 4 on the number line, right? 3.9 lives somewhere around here. Oh, look, that rounds up to 4. Again, where it gets uncomfortable is we start doing negative numbers, right? If I asked you to round up, let's say, a negative 1.7, right? Well, if you look, this is going to round up to a negative 1, because if you look where these numbers are, negative 2 is down here, negative 1, here's your 1.7. Rounding up would be rounding to the right. Remember that just like with the greatest integer less than function, if I ask you to round an integer value, it just rounds to itself because it's already rounded, right? It's already an integer value. Cool. So what we'll do is we'll walk through a couple quick examples. We're going to start this off with E6 and P6, where I just have you evaluate a few of these. So let's go ahead and go over to another slide. So for E6, we're just going to go ahead and evaluate. And I think if I can manage to get everything to fit in, I'll put a P6 here too, so we can just get them both done. So we're going to evaluate. Cool. All right, so let's do A, B, C, D, and E for each of them, assuming I can get all those to fit in. Again, I'm trying to get better at writing on this thing. I'm much more comfortable on a random whiteboard sitting on the floor. I mean, not like physically comfortable, because again, I'm a dinosaur, so that was uncomfortable, hence the reason to try and improve. Okay, so let's do the round down function of a 3.2. We'll do it is much harder to draw when you're used to drawing brackets that are like full-on brackets. It's hard to condition yourself to draw just the round up or round down ones. I'm going to throw that out there. Let's do cool. All right, so that'll be our E6, right? So we've got and we'll talk about the brackets in a second. Let me give you a couple similar ones for this. Sorry, that is meant to only have the top bracket, but again, sort of hard to draw sometimes. And then for this one, again, top bracket only. Let's do, sure. Okay, cool. So let's walk through these. So again, you don't have to do it, but I find it's helpful to draw the little number line. You don't have to. I'm just going to put a little number line here for all of them. Okay, so for this one, 3.2 lives between 3 and 4, right? There's 3.2. This is a regular bracket, which means it's a round down function, so my answer is 3. Here I've got a number that's between 10 and 11, right? 10.8 is here, and this is a round down function, right? Because it's bottom brackets only, so it's a 10, right? Here I have a number that's between negative 52 and negative 51, right? It lives somewhere around here, and that's the round down function. It's the regular bracket, so it's a negative 52, right? Here I have a number that falls between 10 and 11, right? It's somewhere like right around here, and that's the round up function because it has the top bracket only, so that's an 11. And here I have a number that falls between negative 104 and negative 103, somewhere around here. That's the round up function because it's top bracket only, so it's a negative 103. Now you can pause me if you want. I'm going to go ahead and walk through P6, but you should do it on your own if you want. And again, if you can do this without the number line, that's totally great, right? If you recognize, hey, this is a round down function, and 52 point something has to be between 52 and 53, and I'm rounding down, great, right? This is a 52. 6.9 is between 6 and 7, right? And again, it doesn't matter where it is between 6 and 7. That's a round down function, so it's going to be a 6, right? Negative 308 is between negative 309 and negative 308. Sorry, it's a negative 308.1, so it's there, sorry. It's the round down function, so it's going to be a negative 309, right? 25.2 is between a 25 and a 26, and that's the round up function, so it's going to be a 26, right? And negative 3.7 is between a negative 4 and a negative 3, and that's the round up function, so it's going to be a negative 3, right? So there you have your E6 and P6. So if we go on to the next page, what we're going to talk about is how these graphs look. So the trick with this is that once you know how this graph looks, you don't have to spend a whole lot of time expecting that this graph is going to look a certain way. So what we're going to do is in our example 7, we're going to go ahead and graph f of x equals the greatest integer less than x, so the typical round down function. And the trick is that when we graph this, we're going to have to pick a couple decimal values, because if all you pick is integer values, this is going to look like a line, and that's not accurate. This is not y equals x. This is going to look like stairs. So what I'm going to do is I'm going to go ahead and start, I'm going to have my x, I'm going to have my round down function, right? I'm going to pick some decimal values. I'm going to start negative. I'm going to pick a couple decimal values between each integer value. So let's go ahead and start with negative 2, negative 1.8, negative 1.5, negative 1.2, negative 1, negative 0.8, negative 0.5, negative 0.2. And I promise, I know this seems tedious, but we're not actually going to do this forever, right? We're just going to do it once or twice to show you how it works, and then that's it. So then I'm going to have a 0.2 and a 0.5 and a 0.8. I don't know why I always pick 2, 5, and 8 as my decimal values, okay? I'm going to make a second table for numbers that are the next set, so my x and my round down function, right? 1 and 1.2 and 1.5 and 1.8. Again, you could pick any decimals. I just like to pick the same consistent ones. So I promise that although this seems really tedious right now, I'm not going to make you do this regularly. I just want you to know what it looks like. 2.8, 3, 3.2, 3.5, 3.8, 4. Okay, so when we talk about what these are going to round down to, I'm going to alternate colors as we go. All right, so negative 2 is going to round down to negative 2. The trick is that all of these numbers are also going to round down to negative 2, because if you picture where negative 1.8, negative 1.5, and negative 1.2 live, they all live between negative 2 and negative 1. So every number in that section is going to round down to negative 2. But then negative 1 is going to round down to itself, right? Because it's an integer already. And so are all of these next set of values, because if you picture all of those, they fall in the window between, so all of these fall the window between negative 1 and 0. So they're all going to round down to negative 1, right? But then if you look at the next step, 0 is going to round down to 0 because it's already an integer, and all of these numbers are also going to round down to 0. Again, if you picture y, right, it's because these are all numbers between 0 and 1, so they would all round down to 0, right? And you're probably starting to picture the pattern here, right? All of these numbers from 1 up to 1 point anything are going to round down to 1. All of the numbers from 2 to 2.8, and it's not just 2.8, it's 2 point anything, will round down to 2, right? Any number from 3 to 3 point anything will round down to 3, and then when I hit 4, it's going to loop back and jump up to 4. So now if we look at what this graph is going to look like, and again, I apologize in advance for being pretty terrible at graphing. I can probably actually have a good idea. Let's see how this works. Oh, this is why they don't put me in charge of typing things. All right. Let's see if that helps. Hey, look at that. All right, see, every once in a while I have my moments. Okay, cool. So now let's go ahead and graph those steps. So what we had here was at -2, right? So -2, I should have a y value of -2, right? So right here, right? And then it should be a -2 up to anything really, really, really close, right? Anything really, really close to -1, but not actually -1. The second I actually hit -1, this graph's going to jump up and have a closed dot at -1. And then it's going to stay at -1 until I get really, really close to 0. But the second I actually get to 0, this is going to jump up to 0 and be a closed dot, and then be at 0 until I get really, really close to 1. But the second I actually get to 1, it's going to be a closed dot at 1, and then over to essentially 2, but not actually 2, because the second I actually reach 2, it's going to jump up to 2 and stay at 2 that entire time. And then the second I actually reach 3, it's going to jump up to 3 and stay at 3 the entire time. And then it's going to keep doing this forever and ever and ever and ever and ever, right? So I only drew some of the steps, but you get the idea that this is going to keep going. So dot, 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 dot. I'm kind of going to be lazy. So now let's look at what this looks like in a calculator. Now in a calculator, you're not going to be able to see the open and close circles. So we're going to clear this out. Let's go back to our y equals. Now this time we don't want absolute value. What we want is we're going to go over to math, right? And we want number, and we want 5, which is integer, right? So that's going to be our int function, and we want x in there. So I close the parenthesis, and I hit graph. And then sure enough, there's my step function. Now here's what's tricky. When you look at this, even if you zoom in, right? Even if I zoom in a lot, right? If I pick zoom in, oh, my bad. There we go. All right, so let's go to zoom, to enter. There we go. All right. Even if I zoom in, you can't see the open and the closed dot, right? The only way that you're actually going to be able to see the open and closed dot is if you hit trace, you'll see that it's got a closed dot at 0, 0, and then it's going to stay at 0, right? And then when it actually hits 1, it's going to jump up. Now, if you're not able to tell that it jumps exactly at 1, if you hit trace and hit 1, you'll see that the closed dot is at 1, 1. And if you hit trace and 2, you'll see that the closed dot, oh, my bad, hang on. Didn't mean to hit 23, guys. All right. You'll see that the closed dot is at 2, 2. So you can see that the closed dot is on this side, which is exactly what it shows you in our picture when you look at what we drew, right? The closed dot in our picture is on the left side. So where the closed dot is going to depend basically on whether it's a round down or a round up function. You're not going to have to graph these by hand very often, but it is worth knowing that this is what a function looks like most of the time. You're going to see these functions in business models, like I described with the long distance phone calls. That's the sort of thing where you see this. Or if they charge you a certain amount per pound, up to 5 pounds, and then a different amount for 5 to 10 pounds, and then a different amount if you're getting hundreds of pounds of something. So then that would talk about rounding, right? So like the first 5 pounds they charge you a flat rate, but any fraction of a pound thereafter they round up and charge you for a full pound of whatever it is, like coffee beans, or I don't know how much coffee you guys need. I need a lot of coffee, but that's the idea. So I'm not going to make you graph a bunch of these functions in general because I think it's kind of tedious. But what we are going to do is I'm going to give you one to graph just to show you what would happen if you put like a number in front of this thing. So let's go ahead and go, I'm going to give you a P7, right? Yep, P7. Okay, so, all right. So for P7, actually, instead of doing one where you put a number in front, let's go ahead and graph the round up function. And this one's going to be a little harder because your calculator is not going to do it for you without some manipulations that you don't know how to do yet. But I want you to try and graph the round up function. So graph f of x equals the round up function. And what you're going to want to do this is the same super tedious process of picking a bunch of these points and seeing what the steps do. But I'll be honest, I graphed a bunch of steps, right? I graphed 1, 2, 3, 4, 5, 6, and like a half steps. You don't have to do that. If I could have figured out this pattern after like 2 steps, right? So you don't have to graph all of them, and that's basically what I'm going to do when I do this in a second. When I do P7, I'm not going to actually suggest that you graph that many points. Okay, so you can pause me if you want. I'm going to go ahead and grab that graph paper again so that we can graph in a sec. It's a little bit smaller than I'd like, but that's okay. I'm going to make it a little bigger, or I'm going to try. We'll see how well it goes. All right, that should make it at least slightly easier to write. Okay, so you go ahead and try and graph that. While you do that, I'm also going to do it. So pause me if you want to do it without me, and we'll go from there. So when I make my table, honestly, I'm only going to graph like 2 steps because I graphed a whole bunch in the last one, and I really don't have to graph that many to get the idea of what's going to happen, right? I'd suggest you graph some negative numbers, but you don't have to. You could just graph stuff in quadrant 1 and then figure out from that what the rest of the graph's going to do. So I'm going to go ahead and graph -2, -1.8, -1.5, -1.2, -1, -0.8, -0.5. Oh, and somebody has probably thought watching this video, hey, Hogan, why do you do so many decimals? Couldn't you just pick 1 decimal in the middle? And you're totally right. I could just pick 1 decimal in the middle of these. The reason I picked multiple is just to make a point to you that it doesn't actually matter how big or small the decimal is, whether it's a 0.8 or a 0.5. And in the case of a round down function, it really doesn't matter. Okay, so -2 is going to round up to itself, right? But then if you picture all the stuff from -1.8 to -1, they all fall between -2 and -1, meaning they're all going to round up to -1. So if I put that in a different color, let's actually make the -2 a different color since I already did all that other work in red. These guys are going to round up to -1, -1, -1, and then -1 rounds to itself. But then in the next section, right, if you picture the numbers from -0.8 to 0, they all live between -1 and 0, meaning they're all going to round up to 0. So these guys are all zeros. And then if you picture the numbers from 0.2 to 1, they all live between 0 and 1. Since this is the round up function, they're all going to round up to 1s. So what's going to happen here is that now the closed dot's actually happening on the end of each step, right? So at -2, -2, I should have a closed dot. But then anything at all after -2 is going to jump up to -1 and stay at -1 this whole window till I hit that closed dot. Then anything between -1 and 0 is going to round up to 0. So I have this open circle, and then 0, 0 is my closed dot. And then anything after 0 is going to jump up to 1. And then my closed dot's going to be at 1, 1, right? And you can kind of, I mean, if you had to graph this for a lot of steps, you could just copy this over and over and recognize that it's an open circle to a closed circle, jump up to the next one, open circle to a closed circle, jump up to the next one, open circle to a closed circle. And you can see how tedious this is. And based on what we've learned so far in a couple chapters of my class, I think you can probably guess why I'm not going to make you do a ton of this, because I just don't want to be here to waste your time, right? So that's kind of how we graph a step function. It's how we evaluate a step function. And again, you're going to see some problems that involve step functions. I'm not going to make you do a whole bunch of stuff with them. Let's do we're going to do an E8 and a P8, just where I show you what happens if you put a number in front of them so that you can see how they work. But that's something that's going to be addressed a little bit more when we talk about transformation of functions in our next section. So let's talk about how this looks different if I put, let's call f of x a 2 in front of the round down function, right? So let's just talk about how that looks different. And again, I'm going to go over and drag that graph and probably do a terrible job at using it, but that's fine. Okay, so again, I appreciate you guys bearing with me because it is very clear to everyone in the whole world that I am not particularly good at using these things. Okay. So let's do this. There we have it. Okay, cool. So I'm going to move this guy up a little bit. That's all I need. Okay, cool. So let's go ahead and walk through what this graph would look like. And I am mostly graphing in quadrant 1 just to save my sanity because there's a lot of, it's kind of tedious to graph this. So I'm going to go ahead and use the cheat now where I recognize that it really doesn't matter a whole lot how many decimals. Oh no, didn't mean to do that. Take that back. All right, so I'm going to go ahead and recognize that it really doesn't matter a whole lot how many decimals I plug in. So this is my x, this is double of this round up function, right? So let's say I go ahead and we'll just use mostly stuff in quadrant 1 to save our sanity. So let's do 0, let's do 0.2, 0.8, 1, 1.2, 1.8, 2, 2.2, 2.8, and 3. That should be plenty to get our graph done. So this is a 2 times what happens when I round up a 0. Well, integers round up to themselves, so that's a 2 times a 0, which is just 0, right? But if you notice, all of the numbers from 0.2 to 1, these guys all live between 0 and 1, which means they're all going to round down to 0. And I said round up in the last one, and I meant round down a second ago. Anyway, sorry, not to 1. So these guys didn't mean to bracket in the 1. So these guys are all going to round down to 0, right? All of these guys. So they're all just going to be a 2 times a 0, which means literally all of them are just going to be zeros, right? But the second I get to 1, right? The second I get to 1 and pretty much 1 to 1.8, these guys live here, 1 to 2. They're all going to round down to 1. Well, that's a 2 times a 1, so they're all going to be 2s, right? Because I'd have to do the round down first, and then the second I get up to 2, right, 2 to 2.8 are going to live between 2 and 3, which means they round down to 2. My bad. All right, so they're going to be a 2 times a 2, which means they're going to be a 4. So what's going to end up happening here, and when we jump to 3, it's going to end up being a 2 times a 3, which is going to jump us up to a 6, right? Because this is going to be 2 times 3 rounds down to 3, so we'll just get 6. Okay, so if we look at what these steps look like, basically what's happening now is we're going to have a step at 0, right, that has its closed dot, and it's going to be 0. But then instead of jumping up 1, and this is the big difference by having that 2 in front, it's going to jump up to 2 and then have the same step, right? And then it's going to jump up to 4 instead of, right, and then have the same step. So it's jumping up by 2s. That's really the difference. So it jumps up by 2, and then if you wanted to continue, you can follow the pattern. Jump up 2, jump up 2, right? And that's the gist. And you could go the other way too. You could jump down 2, and so on, right? So that's our step function.